We're still in 4.1, and we're continuing with percentage error, relative error, and so on. So far we discussed this error, the absolute error that happens. So you have one measurement, and then you have an error in that measurement, and then you use that measurement to find the value for another quantity, basically, by plugging it into a function. Now, so let's see, this is the measurement that may have error of delta x. And so you want to know that the error would have been the difference between these two, right? And so we approximate that with dy. Now, the question is, this dy could be big or small, or delta y could be big or small, but it really matters how they compare to the actual value of the function that we're getting. So the comparison, the relative error, is the important part of it. And that's why the relative error comes in. So percentage error is equal to error of f over value of f at a. So it's delta f over f of a. Okay, but then delta f, we decided that can be approximated by df. And what is df? df is just f prime at a times delta x. And therefore, percentage error is just f prime delta x divided by f of a. And then you have to multiply it by 100 and write it in a percentage form. So this gives you a decimal, and then you use the ratio. So let's do an example of percentage error. Example 4, using a ruler marked in millimeters, you measure the diameter of a circle as 6.4 centimeter. Diameter, let's show diameter d. This is going to be the measurement that is going to be the input. And then it says how large can the error in the calculating area of the circle be. Let's remember how area is related to d. Area at r is pi r squared, but r is d half. So it's going to be pi d squared divided by 4. So a at d is pi fourth, that's the constant coefficient, times d squared. So now it's asking how large can the error in the calculating area of the circle be. Now, d is measured 6.4. That's the a. That's where we put the tangent line at. But d is going to sit between 6.4 plus 0.1 millimeter, 0.1 centimeter, which is 1 millimeter, and 6.4 minus 0.1 centimeter, which is, this part is 1 millimeter. And so this is actually basically telling us that delta d is equal to 0.1. Okay, and the absolute value of delta d is maximum 0.1. Now, the question is, how do I find the error? Error is delta a, and delta a is approximated by dA. What is dA? dA is derivative evaluated at the a, which is 6.4 times delta d. What is the derivative? Let's change color. Go from, this is the function, so a prime of d is going to be pi fourth times 2d, which is pi d divided by 2. Then plug in 6.2, so I get pi half times 6.2 times delta D, which is 0.1. And then if you multiply all that together, you get pi times 0.32. And then you can calculate the absolute, the approximation of the absolute error. Now, the next part is we want to find the potential percentage error. So what we get in here, we can calculate it using our calculator. We divide that by the measured area, the area that we measured, which would be plugging in 6.4 in the area formula. And then we get the percentage error. So let's go over here. Multiplying these together gives us 1.01. And so delta D, the absolute value of delta D is 1.01. You put a plus minus in front of it. And then you plug in 6.4 into this formula. So pi 6.4 pi times 6.4 to power 2 divided by 4 will give you this value. And so you divide the error that you found using dA divided by the value you found by plugging in the measurement in the function, and you get this value. Write that as a percentage, and that gives you the percentage error that you need. Now let's talk about effect of concavity in approximation. So the accuracy of an approximation using tangent line is affected by the concavity of the curve. At a point A equal to A and f of A, if we are concaved up, let's see, here's a concave up, tangent line would go under. And so when this is going to happen, the approximation is a lower value than the value of the function. If it's concave down, then the tangent line would go above it, so approximation is above the actual value, so it's higher, so it's over approximation. What if there's an inflection point, and one side you can have values bigger, one side you can have values smaller, and the other thing is that the greater the absolute value of f double prime A is, the more graph diverges from tangent line, gets away from the tangent line, so the approximation kind of fails. So we like f double prime to be the absolute value of f double prime to be closer to 0 rather than a big number. Okay, example 5. Use a suitable linear approximation to estimate a natural log of 1.1. Is your estimate greater than, less than, or equal to the actual value? Okay, natural log of 1.1. In grade school, what would, first of all, what is the function that I'm using? Here it seems like y equal to natural log of x is the function. Now, if I was in grade school, what number would I use to approximate natural log of 1.1? I would do natural log of 1 because I know what natural log of 1 is. Natural log of 1 is 0. And so using all of that, how do I approximate? And the first thing first, I want to take the derivative, 1 over x. So this is a, this is the function, that's the derivative, 1, 2, 3. Plug in the a into the derivative and find dA for. So the change dA is dy is equal to 1/1 times delta x. What is delta x? Delta x is 0.1. So let's go to 0.1. And then 5, the value is going to be natural log of 1 plus 0.1. Okay. That's one method. This is actually, this is approximated, sorry, the value approximated by natural log of 1 plus 0.1, which is 0.1. This is one way of dealing with this. The other way is just writing the linearization down. So let's write the linearization down also. So the second method of doing this is write it down as linearization. Again, the information that you got in here and is going to be what gives me natural linearization at 1, because a is 1 of 1.1. That's what we want to find. And so linearization at 1 of x is equal to f at 1, which is a, plus f prime at a times x minus a. A is 1, f of 1 is 0, f prime of 1 is 1, x minus 1, x is 1.1. Hold on, this one was this, so L1 of 1.1 is going to be 0.1. And that's the approximation, and these two values match. Now that we found an approximation, let's figure out whether or not this approximation is overestimate or an underestimate. To find that, you have to use your second derivative, and second derivative is going to be x to power negative x to power negative 2. See, the first derivative is this. Take another derivative of it, you get that. And then as x approaches, it's basically as h approaches 1, and then for any x, this is basically negative 1 over x squared, and it's always negative value. That means that we always have concave down. Concave down means that the tangent line, the values on the tangent line is overestimate for the value that we have. And so that tells me about the overestimation. And so in fact, the value of the natural log of 1.1 is given here, and it's slightly less than what we found.